Assalamu alaikum wa rahmatullahi wa barakatuh. Hi everyone. Today we are going to solve three special problems at the same time from the book of the Professor Cornell from Romania. And the book is Almost Impossible Integrals, Sums and Series. And these are our problems that we are going to solve. Two integrals and one sum. I am Mr. Sherif Hamid with you, math and mechanics teacher, works at STEM Kafr Sheikh High Schools in Egypt. Let's consider this integral to be I1 and with the positive sign inside the len to be I2. And I will start with I1. I will consider the Feynman method. Please revise my previous video about the Feynman method. I will consider that Im equals half times this integral, and if I took a derivative with respect to m, and after that substitute m with 0, I will obtain the original one, which is I1. So I can make integrate by parts, and this value will equal 0, so we will obtain this value, and this one will remain, and also, I can use the series for the len 1 plus x squared to make it simplified in the integral, and of course integrate from 0 to 1 x power 2k times 1 minus x to the power m minus 1 dx. This is a very famous integral and it's called beta function, and beta function is connected with gamma function, and you can search the internet for the relation between them. So from this point, this is our main integral, which is I1, and the integral is ready to make a derivative with respect to m. And please consider that the value negative 1 power k, gamma 2k plus 1 divided by k, all of these values are constant if we are making a derivative with respect to m. So after making a derivative, we reach this point with respect to m, and after substituting with m equals 0, we reach this value, and it is so similar to my previous solution of the previous problem, if you remember. And after simplifying, we reach this value, which is the value will equal half sum k equal 1 to infinity negative 1 power k divided by k Euler constant plus polygamma function 2k plus 1. And here the magic happens that the polygamma 2k plus 1 equals negative Euler constant plus harmonic number 2k, and here we obtain this value. And from the properties of the harmonic number and its relation with integration, there is a very famous identity which exists in the book of the Professor Cornell, and it is easy to make a proof for it. And by make some modification for this identity, we reach this level. Sum k equal 1 to infinity negative 1 power k divided by 2k, harmonic number 2k minus harmonic number k, as I took the sum as a common factor, equals integrate from 0 to 1 len 1 plus x sum k equal 1 to infinity negative 1 power k x power 2k minus 1 dx. And from the properties of the sum, the value of sum k equal 1 to infinity negative 1 power k x power 2k minus 1, it is the same as integrate from 0 to 1 x len 1 plus x divided by 1 plus x squared dx. And here is also a magic happens that this value, it is the same as I2. So when I2 go to the other side, and this one is the same origin I1, we find that I1 plus I2 equals sum k equal 1 to infinity negative 1 power k divided by 2k harmonic number k. And this is the first relation between the three problems, that the sum of the two integrals equals half of the series of the harmonic number. Let's continue our solution, and we will move to the sum of I1 plus I2. Of course, from the properties of the len, their sum equal integrate from 0 to 1 x len 1 minus x squared divided by 1 plus x squared dx, and by substitution substitute x squared with x, so the derivative of x squared is 2x dx, so the integrate will be converted into this form, and we can substitute x with 1 minus y divided 1 plus y, and this is a very useful tool in such a problem. When x integrate from 0 to 1, you will find that this tool will be very useful, and when we substitute, you will find that we will reach this value after simplifying. Half integrate from 0 to 1 len 2y divided by 1 plus y divided 1 plus y dy, and after expand the len, we find that we find this value. And of course, all of these are very simple, and you can make an integrate. So the value will equal 1 over 4 len square 2 minus pi square divided by 24. And as I said, this is the second relation between our three values, and this is I1 plus I2. Okay, how about I1 minus I2? When we use also the properties of the len, we will find that it is equal from 0 to 1 x len 1 minus x divided by 1 plus x divided by 1 plus x squared dx. Also, we can use the same tools that we already used to make it simplify. So we will reach this point, integrate from 0 to 1, 1 minus y divided by 1 plus y times len y divided by 1 plus y squared dy, and after make a partial fraction and factorize these brackets together, we reach this value. We have two main integrals here. I will consider this one is double I, and the second one is triple I. Of course, this is just a symbols to make it easier for us. So double I, and I will use the 1 divided by 1 plus x to make the Taylor series for it, and it will equal sum n equals 0 to infinity negative 1 power n times integrate from 0 to 1 x power n len x dx. After making integration by parts inside the sum, we reach this value. Of course, this one will equal 0. And after making the famous series of 1 divided by 1 plus n squared, the value will equal from the Euler sum will equal negative pi squared divided by 12. So this part equal negative pi squared divided by 12. How about the second one? The second one, it is the same idea. We will make integration by parts. We will reach this level, and by also using the sum Taylor series of len plus 1 len 1 plus x squared, we will find that it will equal at the end negative pi squared divided by 48. And after we substitute these two values in these integrals, we will find the third relation, I1 minus I2 equals negative pi squared divided by 16. And let's consider the previous relations. I1 plus I2 equals sum k equal 1 to infinity negative 1 power k divided by 2k harmonic number k, and also I1 plus I2 equal 1 over 4 len square 2 minus pi squared divided by 24. After we solve these relations, if I add the first one with the third one, we will obtain I1, and then substitute with I1 to have I2, and in the second relation, after substituting, we will have the series harmonic number. I hope that you understood these three problems very well, and I will see you soon with another video in the advanced level. Thank you so much.